So we've talked what it means for a point to be an isolated point, what it means to be an interior point, what it means to be a boundary point. But now let's talk about sets. So a set E in the complex plane is going to be called an open set if E contains only interior points. So if every point in E is an interior point of E, then it's called an open set. And so these are sets that look like this. So no matter what point you pick, if you zoom in enough, you can find some open neighborhood, some open disk centered at that point that stays inside the set E. So those sets that have that property are called open sets. Again, every point is an interior point. A set E is closed if E contains all of its boundary points. Okay, so there's other precise ways to do this. It turns out actually that a set E is closed if and only if the complement of that set is open. And then open sets we've defined above. An equivalent way is just to say that a set E is closed if E contains all of its boundary points. Okay, and so this is where the terminology really comes from. If we look at the pictures long enough, you can imagine that this is kind of a set with an open border. And so that's, you call those open sets. Completely closed border, those are closed sets. And then one word of caution, not all sets have to be closed or open. And in fact, there's two sets that are both closed and open, namely the complex numbers and the empty set, which I'll talk about in just a second. To give you an example of a closed set, we can talk about the closed disk of radius r, and that's going to be denoted by d of AR, but we're going to put a bar over it, which I'll explain shortly. So this is the set of complex numbers such that the modulus of z minus a is less than or equal to r. Okay, so we include the less than or equal to. That's the difference between the open disk and the closed disk. So the open disk is just a strict inequality. Closed disk is that less than or equal to. Again, the only sets that are both open and closed are the complex numbers and the empty set. Okay. The empty set is open and closed if we think about, so if we think about what it means with regard to the complement of the set. So the complement of the complex numbers is the empty set. So since the complex numbers are open, then the empty set is closed, and vice versa. Since the complex numbers are closed, then the empty set is open. So there's really no choice there. But those are the only sets that are both open and closed at the same time. Again, many sets are not open and not closed. So I understand where the terminology comes from. It's kind of like you can think about it as having an open border and having a closed border. And many sets have kind of a mixed open border, mixed closed border. Okay, so they're not open and they're not closed. That's totally fine. I'm fond of the saying from a famous topologist. I'm fond of the saying that sets are not doors. Okay, they're not obliged to be open or closed. And here's an example of a set that's neither open nor closed. Okay, some of the boundary is included, some of it's not. Okay, so that's just one example, and there's many other examples that you can concoct that are neither open nor closed. All right, so that's the basic terminology there for sets. A little bit more to talk about. Given E, so given some set in the complex plane, the boundary of E, so the boundary of E, which is denoted by delta E, not delta, del E. This del is the del that you see in Calc 3 with partial derivatives. So this is denoted by del E. So that's the boundary of E, and this is the set of all boundary points. So this is the set of all boundary points of E. Okay, that's what the boundary of E is it's the set of all the boundary points. So not anything too mysterious there. So if we go back up to our example, and we think about this set here, the boundary would be this whole set of boundary points all the way around. Whether it's in the original set or not, doesn't matter. The boundary is all those boundary points together. Okay, so that's what the boundary is. Okay, so that's the boundary of a set E. The closure of E which is going to be denoted either with a bar or is CL of E for closure of E. So the closure of E is E union its boundary. Okay, so the idea is that you take the set E and then you add to it any of the boundary points that are missing. And then that set altogether is called the closure of E. This is the smallest closed set containing E. What I mean by smallest is that any other closed set containing E has the closure of E as a subset of it. So for example, the closure of this set, if I were to take this set, the closure would be kind of just filling in all the boundary points. And then that's the closure of the set E. And if I were to pick any other closed set that contains E, it must have the closure of E as a subset of it. Okay, so that's what I mean by smallest. Smallest in the sense of containment, set containment. Okay, so that's called the closure of E. What else do I want? The interior of a set, which is going to be denoted by E naught or usually int of E. And in fact, the book uses int of E and this E bar notation. So I think that's what the book is going to use. This E bar notation being the closure, that's why the closed disk of radius R had that bar over it, is that we're talking about the set closure of the open disk. Anyways, the interior of E is the set E, but take away all of its border. Okay, so it's the set E minus the border. What I mean by this is it's the set of elements Z that are in E, and Z is not on the boundary. Okay, so that's the interior of E. So again, if you were to draw some maybe half open, half closed set, the interior would be nothing on the border and everything in the set. Okay, so that would be the interior of the set E. Okay, hopefully that picture makes a good amount of sense. The interior of E is actually the largest. This is the largest. Let me use the book's notation. Sorry, I'm fighting against my own memory here. Against my own habits, I mean. The interior of E is the largest open set contained in E. Okay, so it's the largest open set that's a subset of E. That's the interior of E. Okay, and so a few just kind of common straightforward observations. Notice that E is open if and only if the interior of E is just E itself, and E is closed if and only if E is equal to its own closure. Okay, so just two quick observations there, but that's basically everything I wanted to say about open sets and closed sets.